Good afternoon, everybody. I'm excited to tell you about a new tool that Certora built, which is called Roundabout. So many of you know about Certora as providing formal verification, which is a very advanced technique. Today I'm going to talk about a much simpler technique that we have implemented in an open source tool, which you can download and play. So please listen, and we'd love to get feedback. So this is a joint work. This is a teamwork in Certora. I want to point out Julian Dolby, who is a scientist from IBM Research, who joined us recently. I want to point out Jaroslav Bendik, who ran our R&D. Nurit Dor, who has been with us almost from the beginning. Shelly Grossman, who is my co-founder. Chandra Nandi, who is leading the R&D in the US. Leo Hoppenheim, who is a security researcher. We have a large security team in Certora, and John Thoman, who is a senior technical developer. So all of this is a teamwork. And the problem, I think, in the area of the crypto is very clear, but it's actually not specific to crypto. The idea is that as a human and in finance, we think about math. But in fact, in reality, computers, especially in the age of cryptography, they think about bits. So there is a gap between the two of them. And this gap has nothing to do with blockchain or even decentralized finance. And this gap leads to errors. And these errors are very, very tricky in cryptocurrency. And the question is, what do you need to do? Do you need to round up? Do we need to round down? Sometimes the answer really depends on the application, and there is no solution. So I'm sure you heard, there have been quite a few hacks related to rounding errors. And you can take a look on Rect. Again, these are not blockchain specific. I took the ones here from Rect, and you see several one of them. You see the big one by Balancer, Kyberswap, and other. These are all rounding errors. So there are effects of rounding errors which are actually exploited by hackers. And the purpose of this talk is to try to prevent that. Of course, you could use methods like fuzzing or formal verification, but this is supposed to be an easier to use technique that we want to deploy. So what do we want to do? We want to build a tool that automatically helps you, and the tool is intended for developers, although of course it can be used by security research or other. But the idea is, as you write the code, we want to alert you about the consequences of rounding errors. And we want to warn you what's going on. So you as a developer, you'll have the decision what is right and what is true. And this is something that allows you to basically make your code more secure while you develop the code. Okay, of course, you can still integrate it, but it's not a bug-finding tool. You should think about it more as a tool for the developer, like a compiler or other method that helps you get your code right. So the key idea is actually pretty old. Many of you probably, I want to see, how many of you have heard of the idea of abstract interpretation? Raise your hands. So it sounds like there are few, but very few. So this is actually a very, very simple old idea that actually developed by Patrick Rousseau. So basically, I don't have a pointer, but the idea is that instead of working, you think of running your program, but instead of running your program on the real number, you write them on some kind of a representation of these numbers, okay? So here you see that we have a program that manipulates integers. And this program has loops, actually. And we don't know how many iterations are there. But even though we don't know how many iterations are there, we can still figure out some properties of this. Okay, so for example, in this example here, you see that the value of x and y can range on arbitrary value. But in fact, you see that we can infer properties of them without running the program. In this case, we can infer that at the loop, we see that x is odd and y is even. And why is this the case? Because we see that x is started odd and y started even, and we see that when we add an even and odd, we get an odd, and we get an even, we get an even. So basically, this is a very simple arithmetic. And this is there, like I can point out, but you see here, this is called lattice. So the idea is there is this lattice, there is this question mark, which means that I don't know nothing, and there is a value of even, and there is a value which is odd. Okay, so how is this related to rounding? So apparently, it seems like actually rounding is very, very much related to these kind of things, because rounding errors actually also accumulate, okay? So this is really a code that we took from a client, and we run this on very things on the client. And you see here there is this function, and you see that, in fact, how do I know which kind of rounding is here? You can think about it. You see, for example, there is this convert ratio, and it's called receive token price div wad down. How do we know it's div wad up or down? Do we need to trust the user? So we don't actually trust the user. We don't know. Our tool doesn't understand natural language. It understands what's inline the code. And so basically, the fact that you are suggesting rounding up is not necessarily say that you are rounding up. Similarly, you don't know that you round down. And more interestingly, when we actually execute the operation, the imprecision can cascade. So you can have imprecision with one level, which will go to another level. So in the solution, we build this tool, and we integrate it into Walla, the IBM tool, and actually now available. And the Walla actually allow you to do things. You can do many things besides rounding errors. And we can basically find this rounding up and rounding down analysis. Okay, so let's see this example. How do we know about the return value? How do we know the return value? How does the tool say? And as I said, the tool doesn't understand natural language. It only understands the code. So we add this lattice, okay? Our lattice is fairly complicated, but if you think about it, it's actually natural. So the bottom value, the value which is the most precise, is exact. It means that the real number and the integer number coincide. And then there is the possibility of up, that the integer number is above the real number, and there is a possibility of down, that the integer number is below. And if you join them, if I have two possibilities, then it's either. So I really don't know. And the worst that can happen, in fact, is intermediate. I'll show you later, when actually I don't know nothing about it. So you can think about it as some kind of approximating the behavior of the program. That's what we are doing. We are approximating of the behavior of the program, and we cascade the value. So you see, we start by the value being precise. This is where the function starts. And you see that we accumulate it. We go precise, precise. I'll show you later. And the idea is, you see now, we see it's round. It is round. It starts precise. You see, then it's round up, and later on it can round down. So we figure out how the values propagate when the program executes. Okay, so let's see this program here. There is this divide wad up. What do we do? How do we know the value? So what we really do, we actually perform what people call interprocedural analysis. The idea is that we analyze all the behavior of the program. So in this case, we have the function divide up, and it's calling actually the function maldiv up. So we look at its behavior. This function is actually implemented in assembly. So what? So we understand the value, the way assembly is executed. And we propagate the value of assembly. And we understand what are the mathematical rules for the assembly to behave as well. So you see the divide runs up, and adding runs, divides run down, and adding adds up. So we accumulate all the values and we compute them. So this is done. So now, what happened to the return value? So you see the return value, it takes the value which is computed by the previous function, and it returns this value. So what do we do here? Again, we look into the implementation of this function. In turn, this function is calling another function. So you see this function is called, and this function is also implemented in assembly. So we understand how the assembly is executed. We understand how the assembly is executed, and we divide rounded by up, it yields down. So this is how we do this abstract interpretation, and we infer these properties of the program as we do this static analysis. So this is, of course, something we do before the program is executed and warn you about the behavior. Finally, what do we do about the return value? So we propagate from the result to the return value. And in this case, you see that we infer that this function returned down. And this is information that we can tell the user, and the user see if this corresponds with her intuition about what this program is supposed to do. And we have actually implemented several patterns. So for example, this is taken from the Morphos code, but we have run it on many existing code. You see that here it's actually inferred the thing that if you take a function and you add a number and you divide it by a number which is smaller than this, then in fact the result is a rounding up. So it infers some kind of good properties of arithmetic. What happens when you have conditional statement? Of course, any interesting program has conditional statement, and conditional statements are fine. So let's look what happened here. You have some kind of condition. Our analysis doesn't need to understand what is condition. So its conservative assumes that both of them are executed. So you have the first case that the value is up. The other case, the value is down. So this is by itself not so bad. It could be happen. For example, you have a deposit, we have a withdrawal, you have something economically which is different. But what happened in this program, on top of it, the program also does division after that. So our analysis gets very, very confused. And what we do with this case, we alert the user. We say, sorry, we don't know, it's indeterminate, and we don't know. We alert the user about this behavior. So that's what we do. And we say round up this flag is what we call indeterminate. It means that we don't know what the analysis. It's not necessarily a bug, but it's something that we want to alert the user about. Now we're getting to more complex program, and we ran it on quite complex program. This is a real example, and you see actually how the analysis work on something pretty real and pretty sophisticated. And you see actually it makes something about quotient, and it actually gives you something tricky about what happened with numeric. And it's tell you that, in fact, there is some kind of tricky divisor. This has to be reviewed by the developer to see what's the intent. Here is another example. It's really a real bug, actually, that you see it's running by this analysis. And in fact, the tool can tell you the analysis because in this case, it tells you that, in fact, it's indeterminate. So in fact, it gives you this, and this is something that we could have been done to prevent this hack. Okay, and how will it do it? So you see, we start by interpreting that it's down. So this is automatically inferred by the analysis. Later on, it finds out that it's either, okay, which is also inferred by the analysis. And finally, you see here it finds that it's either. And here we see that the user will automatically see that there is a bug, because you see the user call it down, because the developer thought that it's rounding down. So this is a mistake of a very experienced Solidity developer that this tool could have automatically prevented. And this bug, unfortunately, was exploited. So this is what we want to do. We want to prevent this kind of exploit before you run form verification or fuzzing or any other method. So this is what we do, and we want to do this thing. I'm wrapping. This is a basic idea. We have implemented quickly because we were really worried about all these bugs. We did some shortcut, like every time when you do something right, and basically we kept some patterns. In particular, we only handle unsigned. We plan to add more, but this is what happened in most of our clients, so we think this is the most important thing. The analysis is sound. It means we can mathematically prove it's correct, but we have to be careful because we have done some shortcut. That the analysis is definitely incomplete in the sense that there are a lot of programs which are good, and this analysis will fail to handle. And this is of course, it's come from fundamental problems in computer science. We cannot solve them. But I think we can make the analysis way more complete, and we need your help to do it. You can extend the analysis to do many things. There are, of course, a lot of related work, in particular our tool, which is very sophisticated, the Certora prover on the EVM bytecode, and also I want to point the DDAB tool. These are more advanced tools, but we wanted to do something much faster, and this is why we did this analysis. the takeaway, this is a roundabout. It's a tool that you can use anytime, and we have it, and there is a QR code that I can show you. We plan to integrate it with many other tools that we are building in terms of the Certora prover and release it in Q2. It's a security tooling. You can use it with AI or with Forma or with any other tool, and it's simple as extendable code. I want to give you some questions, so time for questions. So basically, this is the QR of the tool. I'm happy to take questions. There is time. I made it talk quick enough. I see that question. Please take questions, please. Yes.
Thank you for your presentation. I'm thinking, would it be possible to compute bounds on the errors? How easy would it be?
Yes, so we have been working, I've been working on it also academically with a colleague at Princeton and Madison. We have method for compute bounds. They're expensive. They are much more expensive than this. This is a very, very simple analysis, and it's even not dying. So the good answers that we have, analysis that we have done, and it's actually very interesting, but it's expensive. And I can tell you, for example, this tool, for good and for bad, it doesn't use the SMT. It's very, very simple. So, and if you want to do that, we can do that, but it's much more complex. This is the way I think about this tool is like, you probably know, I mean, Certora is doing a lot of things, including services, and the service company, we want to find bugs, and we don't want to miss bugs. That's and this is something that is very, very low-hanging fruit for not missing bugs. But you want something more advanced, which we are working on, sort of computing bounds. And in fact, we have been working on it both academically and practically, and we love to talk about it. Thank you.
Thank you so much.
There was more question.
Have you tried running this on the other hacks of a Rect leaderboard, and does it also?
Yeah. We need more, and we will have to. This tool should be available now. I don't think we went into all of them. Hopefully, people will not abuse it. We don't know, but yeah, it is detecting things, and of course, there are some cases that it detects errors, even in programs which are completely right, which is unavoidable, and because it's conservative. It's just basically compute something more of it. But yes, it is a tool that you can use, and I've one of the examples, actually two of the examples are from real hacks.
Thank you.
There's more question.
Thanks so much for the presentation. Sometimes the developers, they have this trick to round up a division of x by y. They do x plus y minus 1.
That's what I showed.
It's the example. And in this case, would the algorithm return up or would it return down?
It's exactly, it knows the value. It knows. So in fact, these are simple cases that we can analyze. Basically, the analysis, abstract interpretation, even though it's so simple, it's surprisingly powerful. We have seen things like McCarthy function, whatever, that sometimes things are very hard for human and very easy for machines. This is something which is pretty easy for machine. The machine only needs to understand that the division by a number which is greater than this number. So it's actually very simple. And that's the thing that, actually I should say, Patrick Rousseau is from France. That's the thing that Rousseau observed many, many years ago, before I even started my academic career. Yes, so the answer is, it's surprisingly how this simple method can actually infer these kind of properties like division by x plus 1. But some things are hard, like, of course, exponentiation. There are some things which are much hard for these kind of things to do. But the normal thing that we see in DeFi should be handled, and we need to see that's, of course, a practical question. But we see that, in fact, it handle division, handle addition, handle assembly code, which is pretty common, handle conditional statement loops.
Thank you.
More questions?
Thanks a lot, and I invite you to continue the discussion just after the session. Thank you.